Welcome to You Got Hope Chemistry. I'm Hope, and you're about to learn some chemistry. Welcome back to You Got Hope Chemistry. In this lesson, we're going to look at voltaic cell design and just voltaic cells a little bit more in detail. All of the base knowledge we've learned in Lesson 1 and Lesson 2 are still going to apply, but we're going to look at subtle nuances, kind of weird half cells, and how do you design a cell. So if you were asked to design a specific cell with a certain electric potential or to have a certain half cell, how would you go about doing that? So not a lot of new, but kind of more detail. So we're going to look at three different things here, looking at voltaic cells and how to interpret them when they look different, picking electrodes when designing a cell, and we're going to actually design a cell. So first things first, not all pictures of voltaic cells look like this. This is your standard salt bridge cell. It is probably the most common type of picture of a cell that you will see. So that's why I use a lot of it in our first lesson. As a recap, one half cell would be in one beaker, one half cell here would be in a different beaker. This is your porous barrier, membrane, separator, however you want to say it. Now this one specifically is called a salt bridge. People also call it a U-tube, because if you tip it over, it looks like the letter U. Okay. We also have a voltmeter here. I know it's a voltaic cell because it has a voltmeter. So we're fairly comfortable with this one. I'd like to look at two different pictures now, and I've added something different than a voltmeter to both of them as well. So the next type of cell we're going to look at is called a porous cup voltaic cell. This is a little bit different. What you end up having is a beaker with one half cell in it. So what I outline in here in blue, this would be one half cell, and this electrode here would be part of that half cell. So for instance, maybe I have something like this is silver solid, and in here I have a silver ion solution with nitrate, and so that half cell would be a silver half cell. The new part here is the cup inside of it. So this here is called a porous cup. They look a little bit like a clay cup, like that was made in a kiln, and they're porous. So they actually allow for the flow of cations and anions from one half cell to another. So I'm going to make something up randomly. I'll call this copper solid. And we can't see it, but inside of this red cup, there would be a copper ion solution, let's say copper 2+ and nitrate again, and that would make up the other half cell. So if I was to do cell notation, just to kind of like practice, this would be a copper half cell. I know that this is going to be the anode because copper is lower down the table than silver. And then we're going to have the double slash. I would have my silver nitrate solution, aqueous, and then silver solid. And that would be my cell notation for this. So that's a porous cup. They don't come up too often, but definitely you would see them on questions online or in your homework. Now the next thing I want to show you is I don't have a voltmeter in the middle of my cell. I have a light bulb. Now, a light bulb can be used to tell whether this thing is actually functioning. So if this produces enough voltage, this should light up. You can do this really easily with a lot of LED light bulbs because they require such low voltage and current in order to operate. But don't be surprised if you see a light bulb as part of a diagram on a voltaic cell rather than a voltmeter. Okay. So that's a porous cup picture. We will do a question today where we use this same picture. The next one, and it's not the last one, but it's the last one I'm going to show you, is a porous membrane. So again, a porous membrane would allow the flow of some things in and out Ideally, it would be ions to allow for anion flow and cation flow. So I'm going to start with this. We do have just one large container, but the large container is separated by this dashed line. This dashed line would be our porous membrane. You can kind of think of it, if you're in bio, like the membrane of a cell that allows some things in and out. Okay, so this would allow for the flow of charge. That would then make this half here a half cell. And then over here, this would be a half cell. Okay, and then we would have two different solutions. So maybe I'll just stick with the silver copper idea. So this would be, say, a silver electrode. I'm making this up randomly. Over here, I have silver ions aqueous. I have nitrate ions aqueous. On the other side, I have a copper solid electrode. And then I have, copper 2+ ions in solution, and put the nitrate ions in solution. So that's a porous membrane picture. These are common. You will come across them. I have also included a different thing other than a voltmeter. I guess this could be a voltmeter or a multimeter. If you've taken physics, you've probably used one, possibly. They measure voltages. So what I have here is 3 lines representing what the voltage would be. So quite often you might see something like, actually, you know what? Let's calculate this voltage and we'll write it in. Okay, so the electric potential of the cell would be the electric potential at silver. At the cathode, 0.80 volts. Minus a positive 0.34 volts. So this would come out to a positive 0.46. You could see something like this where they go 0.46 volts in the multimeter, and then you're told that this is an unknown half cell. What's in this half cell? Because you know the potential of the cell and you know the potential at the cathode. You could figure out what this half cell was, if that makes sense. The next thing we're going to look at is starting to build voltaic cells, and how would you choose electrodes depending on the type of solution you have, or depending on what your oxidizing and reducing agent are. So we'll start with the easiest of them. Most half cells simply have a metal in its own corresponding metal solution. So this is the ones that we have been working on previously. Things like I have a silver ion solution and I have a silver electrode, or I don't know, we have a tin solid electrode and we have tin 2+ ions in solution. If you're going to use silver or copper or tin or lead or whatever it might be, just put it in its own solution, and that keeps everything much more simple. There are circumstances where you can mix different metal electrodes with a different metal solution. We just don't come across it, and don't cross that bridge. We're going to leave that completely alone. If you have copper, you use a copper solution. If you have tin, you use a tin solution. So easy peasy, not much more to explain there. Number 2, this is the big one. When do I use something called an inert electrode? So for everybody who doesn't know what the word inert means, it means it doesn't do anything or doesn't participate, doesn't become part of the reaction. Okay, so inert means you don't do something. If somebody's really an inert person, they probably just sit around and do nothing. So we use inert plastics to hold chemicals because they don't want those plastics to react with chemicals. That's what the term inert really means. So there's 2 types of inert electrodes we really come across, which are carbon solid. This would be graphite carbon, or platinum. Literally pencil lead conducts electricity. So what's the point of using an inert electrode? The majority of the time why we're using an inert electrode is we're using oxidizing and reducing agents that don't have a corresponding conducting metal. So things like acidified permanganate. Well, that's an ionic compound. It's acidified. It doesn't have a corresponding metal. Or how about nitric acid? Nitric acid is a really strong oxidizing agent, but it doesn't have a corresponding conducting material to go with it. So what you do is you just pick platinum or carbon and you use that as an electrode. So for instance, let's imagine that I have nitric acid as my strongest oxidizing agent. So that would be HNO3, which would break down into H plus and NO3 minus. And we wanted our strongest reducing agent to be hydrogen peroxide, liquid. Both of these are aqueous solutions, or if hydrogen peroxide is pure, it's liquid. Neither of these two things have a corresponding metal that or solid that conducts. So I'm going to use a inert electrode in both of these half cells. So for instance, I'll put platinum over here, and I'm going to put my nitric acid in solution. So I'd have H plus, and I would have NO3 minus. And on the products, or sorry, on the other half cell, I'm going to put in H2O2 liquid. Now, a common question I would get here is, what happens to the anode? Most of the questions we've been doing, the anode has lost mass. Now, if an electrode is going to lose mass, it's going to happen at the anode, but this isn't true all of the time. You have to have a solid actually becoming aqueous ions. So if I look at these two half reactions on my reduction half reaction table, I'll show you this. So looking at my reduction half reaction table, I can see my strongest oxidizing agent, nitric acid, and I can see my strongest reducing agent, hydrogen peroxide, on the table. The strongest oxidizing agent is above the strongest reducing agent, and so we are going to have a spontaneous chemical reaction, which is important because this is a voltaic cell and it has to be spontaneous. So my strongest oxidizing agent is here. So I know that this gains electrons, undergoes reduction at the cathode. Now, that is a piece of platinum solid. The cathode is the platinum. It's not necessarily the strongest oxidizing agent. So again, the strongest oxidizing agent reacts on the piece of platinum, which is the the cathode, but it doesn't have to be the strongest oxidizing agent. Conversely, this is my strongest reducing agent, and we know that it loses electrons and undergoes oxidation at the anode. It doesn't mean that this is the anode. It isn't. It's just the strongest reducing agent. But where it will react is at the anode, which is a different piece of platinum solid. So I can have two pieces of platinum as electrodes. They aren't reacting. They're just where the reaction takes place. So for instance, on the cathode, these two things would bump into each other, accept two electrons, and they would turn into N2O4 gas and into water. So the cathode isn't going to gain mass. On the cathode, we're going to see these bubbles form. On the anode side, the hydrogen peroxides are going to bump into its platinum anode. It's going to lose two electrons, and it's going to turn into hydrogen ions, which will decrease the pH, and it'll turn into oxygen gas, which will cause bubbles. What you'll notice is we're not taking a solid and turning it into aqueous ions. We're taking a liquid, turning it into aqueous ions, and we're turning it into a gas. The piece of platinum is unaffected because it's not part of the reaction. All it's doing is allowing for the exchange of electrons to happen on its surface. So one more time, if you are going to gain mass, it's going to be at the cathode, but you don't always gain mass. In this case here, we have aqueous solutions turning into a gas and water. I'm not taking ions and turning them into a solid, like let's say silver right below. If I started with silver ions and I turn them into silver solid, I would be gaining mass. Okay. In this case, there is no gain of mass. We're just forming bubbles, and we're changing the pH because we're using up the hydrogen ions. This thing would become less acidic. On the anode side, we're taking hydrogen peroxide liquid, we're turning it into acid and oxygen bubbles. We are not taking a piece of solid and turning it into ions. I'm going to use silver here again. If I had silver as an anode, it would lose mass because I'm turning a piece of solid into aqueous ions. So please remember, when you're doing evidence at anode and cathode, you gotta look at the whole half reaction on that side to determine what the evidence is. It's not always gaining mass and losing mass. So to help you deeper understand what we just talked about, we are going to write our half reactions in on our notes here. So over on the cathode side, because this would be the cathode, because it contains the strongest oxidizing agent in this half cell, the half reaction would be 2NO3 minus plus 4 hydrogen ions plus 2 electrons makes N2O4 gas plus 2H2O liquid. So the evidence that I would see here is the production of gas, and on that electrode you would start to see bubbles forming. I would also see a pH increase because I have consumed this hydrogen ion here. There is no gain in mass because there is no solid forming. If we go over to the other side where the hydrogen peroxide is, and I write out the oxidation half reaction for hydrogen peroxide because I know this is the anode, since this is the strongest reducing agent, and the strongest reducing agent is on that half cell. So I have H2O2 liquid turning into oxygen gas plus 2H plus aqueous and 2 electrons. So again, I'm seeing bubbles form. These bubbles are oxygen bubbles because I'm producing oxygen, but I would also have a pH decrease because I'm forming hydrogen ions which are acidic. Again, the platinum and on both sides are acting as electrodes, but they're not participating in the reaction other than acting as a surface for electrons to be transferred. The next thing we're going to look at is quite weird and different. It's not very common, but I feel like it's necessary to talk about since I have seen it on exams and practice questions, etc. So I'm going to talk about the Hoffman's apparatus, which is used to collect gases when we talk about electrolytic cells. But what I want to talk about is a gas tube, which is used when you have a gas as a reactant. So I picked out an example half reaction out of the data book. So this is oxygen gas and hydrogen ions working together to form water. And I'm just going to throw out that we want to make a cell, and let's say the cell had this as the strongest oxidizing agent. The question becomes like, how do I get oxygen into an acidic solution? I don't physically know how that is possible. So I'm going to give you an imaginary cell notation to help you better understand what this would look like. So let's say we had zinc as our anode. So I'd have zinc and then say maybe zinc nitrate solution on my anode side. I'm just completely making this up. And then how this would look like in cell notation would be something like this, like O2 aqueous, H plus aqueous, and then they may or may not throw in an anion in there. There would have to be one, but there may or may not be in the actual cell notation. And then because there is no such thing as solid conducting oxygen gas or hydrogen ions, then I would have to use platinum or carbon, and I'm going to just stick with platinum on this one. So I'm going to use the speaker as the half cell for this side. I'm not going to draw out the other side. So this would be this half cell. It's the same thing. So first of all, it would have to be filled with a solution which is acidified. So I'm going to put H plus in here. Again, there probably is an anion in there. I just don't know which one. And then I need something to force gas into the solution. And so a gas tube kind of looks like an inverted test tube, except it has a little spigot coming out one side. And then it comes down. So it kind of looks like a test tube. Like a test tube would look like this. Obviously the other way around. It wouldn't have the little spigot on it. And then what you would do is you would connect this little nozzle to a hose. And that hose would be pumping oxygen gas into that tube. And this would just connect to a big gas cylinder of oxygen, or if you were in a really nice fancy lab, you'd probably have oxygen coming out of basically the same thing as gas would come out of. Now, through the top of this, there'd be a little hole drilled and a metal rod put through it. And then you'd have a little platinum electrode. This would be a tiny piece of platinum solid. So again, the oxygen, I'm going to actually make it pink here. This oxygen is going to get forced down and it's going to bubble past this platinum electrode. The hydrogen ions would hit that oxygen here and they would react and you would get that half reaction. So this is quite rare. I did want to show it just in case you were curious when you were doing questions and you noticed you have solutions which contain a gas. This is how that would be done. So what we're going to do now is we're going to construct a cell that would require to have 2 inert electrodes based off of these 2 half reactions. So I picked these 2 because there is no solid metal to go with the strongest oxidizing agent or the strongest reducing agent. So I simply took these clips from the reduction half reaction table. You notice that this is a larger positive electric potential and this is a smaller. So my SOA would be up here, my WOA here, my SRA here, my WRA here. So the spontaneous reaction would happen between the bromide and the acidified perchlorate, which is perchloric acid. So this is a spontaneous reaction between the 2. Well, this strongest oxidizing agent here, it doesn't have a solid to go with it. So I'm going to pick a platinum solid for it. And I recognize that this is going to gain electrons, undergo reduction at the cathode because this is my SOA. And then over here, I'm going to pick, I'll just pick carbon. No particular reason, just we haven't used it yet, as my electrode. And remember that this is going to lose electrons, undergo oxidation at the anode. It is the Ra, so my carbon electrode is going to be my anode. I'll pick one side to be the anode, one side to be the cathode. Arbitrarily, I'll make this the carbon solid, which is the anode. I'm going to make this one platinum solid. This is going to be the cathode. And then I'm going to include my solutions. So on my cathode side, it must be acidified, and it has perchlorate in there as well. On the anode side, I am going to include everything that is actually I'm going to include chloride here as well. I'm going to include everything that's in the half reaction. So I'm just going to scroll up here. Normally when we have, say, a metal and a metal solution, we have everything in the half reaction. So for instance, you might have something like silver ions and a silver solid, and I would see all of that in that half reaction on that side of the half cell. I'm going to do the same thing here. I'm going to include everything that's in here in this half cell, and I'm going to include everything in here that's in this half cell, even the chloride. So I've added the chloride there. And I'm going to have on this side bromine liquid. It would probably sink to the bottom. I'm not 100% sure. Bromide ion. And I'm going to use sodium as my cation. I'm going to say sodium bromide was dissolved. This could be potassium bromide or anything that is soluble. Now that we have the basic structure together, we can do all of our flows. So we know that electrons move from anode to cathode through the wire. So that would be my electron flow. We know cations like to move towards the cathode because that's where the negatives are going. So I could have my hydrogen ions going that direction, my sodium ions going that direction. And I have to have my anions going towards the anode. So I'm going to have the ClO4 minus going this direction, the Cl minus going this direction, the Br minus going this direction. So there's our 3 sets of flows. Then what we should do is we should include our reactions on each half cell on that side. So over here I have ClO4 minus aqueous plus 8 hydrogen ions aqueous plus 8 electrons, and that's turning into Cl minus aqueous plus 4 waters. On the other side, I would have Br minus, 2 Br minus aqueous turning into Br2 liquid plus 2 electrons. Now I am going to have to multiply this side by 4 in order to balance out the electrons. I'm going to multiply this whole half reaction by 4 because I need 8 electrons to balance it out. So this would actually be 8 Br minus, 4 Br2, and 8 electrons in order for those electrons to cancel out. All right. The next thing we should do is we should do evidence at each electrode. So I'm going to start at the cathode side. I begin with hydrogen ions, which are acidic, and in the product I have no hydrogen ions. So I know that the pH is going to increase because I am consuming acid. I look for anything else like bubbles, no gas being produced. I look for solid being produced, no solid being produced. Okay, pH increase, that's it. Let's go to our other side. I'm taking bromide ions and I'm turning them into bromine liquid, Br2 liquid. Now in the first half of redox, we learned that bromine liquid is an orangey brown or a yellowish brown or a reddish brown, something like that. And so what you would actually start to see is some Br2 building up on that electrode, and it's going to look darker here. It's going to be a bit orangey brown, yellowish brown, something like that. As long as the the word ends with brown. So yellowish brown, orange brown, reddish brown, those are all fine for that one. That's something that had to be memorized. The next thing we can do is our electric potential for the cell. So we know that the electric potential of the cell is equal to the electric potential at the cathode minus the electric potential at the anode. And so we've got a positive 1.39 volts minus a positive 1.07 volts. And some mental math there, 1 and 7, that's going to be 0.32 volts positive. That's my electric potential for the cell. The last thing we can do is we can put the 2 reactions together and come up with a net reaction. So the net reaction for this cell would be ClO4 minus aqueous plus 8 hydrogen ions aqueous. The electrons would cancel out. 8 Br minus aqueous producing Cl minus aqueous, 4 H2O liquid plus 4 Br2 liquid. Okay. If we check our charge, I have 1 times -1 is -1, 8 times 1 plus is 8 plus, 8 times 1 negative is 8 negative. This is a total of -1. This is -1. This is 0. This is 0 for a grand total of -1. So there we are. our entire cell complete. All the questions we could possibly be asked done. Let's try building a different type of cell. So what we're going to look at next is constructing a voltaic cell that has some kind of restraint or constriction on it. So for instance, we're going to construct a voltaic cell that produces a voltage of at least 0.50 volts. That shouldn't be too hard to do. I'm going to pull up the reduction half reaction table in just a moment so we can pick out something to use. What I do want to point out though here is this little side note, okay? It's actually quite important. You just can't be picking whatever you want to make a cell. So my suggestion is to never use a half reaction that falls below 0.83 volts on the reduction half reaction table. Now the significance of that is that water is an oxidizing agent at that spot. So let's go to our reduction half reaction table and I'll explain why. So here we are at the reduction half reaction table, and I'm going to highlight that very specific half reaction I was talking about. So at negative 0.83 volts, water is an oxidizing agent. I don't want to construct a half cell with anything below here for the following reason. Let's say I was going to use iron as my cathode half reaction. So let's say this is my strongest oxidizing agent. This would be my cathode, and I wanted to build a cell. Well, that means I have to pick a half reaction that falls below here. Now zinc would be a good option. This would be then a strong reducing agent, and I can have a strong oxidizing agent. Both of these things have a metal solid to make a cell with, and the reaction is spontaneous. Now the voltage it would produce wouldn't be that big because there's not a big difference in potential on the side. So for instance, in our question, I couldn't use these two half cells because they wouldn't produce a reduction potential of 0.5 or over. So students might say, well, I'm just going to go lower. Mr. Hope, why don't I just go with an iron lithium battery? There's a huge difference in potential. I'm going to be way over the 0.5 limit. And my answer to you is that this has water in it. Water is right here. And if I was to take a piece of lithium and drop it into water, it would explode. It would react with that water so fast, producing hydrogen gas, very exothermic, and it would blow up. I cannot be using these metals specifically more than the others to build a half cell and to have these on the anode side. Most of these react violently with water. So I can't build a cell out of them, at least not an aqueous cell. So a lot of you have heard of lithium-ion batteries. They are very good batteries. They produce a lot of electricity, but they're not an aqueous battery, which means they're not dissolved in water. When we're building an aqueous battery, we cannot use this stuff. So when I design a cell to produce a voltage, I'm staying away from chromium, because if I put chromium into an aqueous solution, it's going to react with the water, and not all of the electrons are going to be transferred to the cathode side. Some of them are going to be transferred directly to water within the half cell. Same thing with aluminum, magnesium, sodium, calcium. This is a very unique spot where I absolutely want to stay away from building any half cell with this stuff below this level. Another one which really doesn't come up too often, but I would definitely stick away from, is mercury. So here's mercury. Mercury is a liquid at room temperature. So if I'm building a cell with a mercury ion and mercury liquid, what am I going to use as my cathode or anode depending on which half cell it's in? this is not solid mercury, it's liquid mercury. So I always stay away from building a cell using mercury as well. So now that we know what we don't want to use, let's pick some stuff that we think we would like to use in order to make this cell. I've highlighted the water again at the bottom of the reduction table. I'm staying away from that. If I want to produce more voltage, then I want to pick items that are fairly far away from one another on the table. I want to pick something easy to work with. I personally don't want to be getting into using platinum if I don't have to. A simple metal ion solution with another metal ion solution would be probably the easiest and safest bet to build one of these cells. So I could do something like maybe a gold cathode side of a battery with almost any other metal combination. I could probably do it with copper. There's a huge difference between 1.5 and 0.34. I could do maybe a silver tin combination that is definitely over the 0.5 minimum. I think maybe I will pick something that has a little bit more evidence change in it. So let's do something like nickel half cell and let's do gold and a gold half cell. Okay, so if I was to do that, the gold would be my strongest oxidizing agent and my nickel would be my strongest reducing agent. And we'll say that both solutions were with nitrate ion. So we'll have a nickel nitrate ion solution and we will have a gold nitrate ion solution. And we'll go construct our cell. So I'm going to get you to try to do most of the work on your own, but we're going to do it a step-by-step process. I'm going to ask you to pause. I'm going to give you a question to do, then you pause. When you're done, you come back and you see if you get it right. So we agreed to make a cell out of gold 3 nitrate and gold solid, as well as nickel 2 nitrate and nickel. So what I would like you to do is I'd like you to fill in the cell notation that would correspond to using these in a cell. Pause now and give it a try. Okay, let's review that answer. We knew that the nickel solid was the strongest reducing agent, and therefore we're going to lose electrons, oxidation anode, Ra. We found out that gold 3 was the strongest oxidizing agent, so it will gain electrons and undergo reduction at the cathode. The anode is always put on the left-hand side of the cell notation, so this should be nickel solid. This is nickel 2 nitrate. You can keep the nickel and nitrate together or you can split them apart. The gold 3 nitrate would go here. Again, I could have it as gold 3 and nitrate and have them separated, or I could put it together. And then gold is the cathode, so it belongs on the outside. Okay, let's go down to our picture. This is going to be a porous cup picture that we're going to work with. Let's assign one side as the anode and the cathode and fill some stuff in, and then I'll proceed with the questions. So let's say that this here is going to be gold solid. Inside the porous cup, I have gold 3 plus aqueous, and I have nitrate ions aqueous. I'm not going to draw them in there because the porous cup, you can't see through it like you could see through a beaker. I'm going to call this nickel solid, and I'm going to put nickel 2 plus ions in solution and nitrate ions in solution like that. Now that our basic structure of the cell is set up, we're going to proceed to ask you to do a few questions. So let's start with the 3 types of flow. I'd like you to indicate the cation flow, the anion flow, and the electron flow. Pause the video now. Now that you had a chance to do it, let's see if you did it right. We know that the gold is the cathode, and we know that the nickel is the anode. So the first type of flow we're going to do is electron flow. Electrons always flow from anode to cathode through the wire, and they're going to pass through the light bulb, which is going to cause it to light up. So there's our electron flow. Cations flow towards the cathode. Now the only cation I have drawn in here is the nickel 2+, so that's going to go towards the cathode. And the nitrate, which is the anion, is going to go towards the anode. So there's our three types of flow. The next thing I'm going to get you to do is I'd like you to write the appropriate half reaction beside each half cell. So I'd like you to write the nickel half reaction over here, and I'd like you to write the gold half reaction over here. I'd like you to make sure that the electrons are balanced for the two half reactions and show the evidence that would happen at each electrode. Pause now. Okay, now that you've had an opportunity to work on it, let's check to see if you did it right. We know that the gold is the strongest oxidizing agent, or I should say the gold 3+. So I'm going to start on this side. This is the reduction half reaction. It's going to gain 3 electrons and it's going to turn into gold solid. The nickel, on the other hand, is undergoing oxidation, so it's losing electrons. So it's the nickel solid that's going to lose the electrons to form nickel 2+ ion, aqueous, plus 2 electrons. Now, in order to balance out the electrons, I need to find the lowest common multiple between 2 and 3, which of course is 6. So I have to multiply this by 3, and I have to multiply this by 2 in order to get 6 electrons on each half reaction. So this would be 3, 3, 6. Gold is 2, 6, 2. So there are our half reactions on both sides. The next thing we need to do is our evidence. Because nickel is starting as a solid and turning into an ion, it's physically losing mass. That solid piece of nickel is getting smaller. So this is going to be a smaller electrode at the end. Gold ions are gaining electrons and literally plating onto the gold electrode that's already there, and it's going to get bigger. So I'm just going to extend this electrode, and I'm just going to say this would actually end up getting bigger. So this is going to have a gain in mass, and this is going to have a loss in mass. Now the other thing that's going to happen here is nickel has a color. Nickel 2 ions, I believe, are a bluish green color. And so if I'm producing more of the nickel 2 ion, the solution which the nickel 2 ion is in is going to get darker. So this is going to become darker blue green. We would see that in this area here, not necessarily in the other half cell. So this is going to start getting darker blue-green. Because it already had some nickel ions in it, it is already blue-green to start. Okay, the next two things I'd like you to do is I'd like you to calculate the electric potential for the cell, and I would also like you to write out the net reaction. Pause the video now. So, the electric potential of any cell is equal to the reduction potential at the cathode minus the electric potential reduction potential at the anode. And so the cathode is gold. Its electric potential is at 1.50 volts. The anode is going to be the nickel half reaction. And now that's minus a negative 0.26 volts. The negative makes it a positive. And so our final electric potential for the cell is going to be a positive 1.76 volts. There is my net cell potential. Just looking at the two half reactions, because I've already got them balanced independently, I'm going to put those together. So I would have 3 nickel solids plus 2 Au3 plus aqueous, producing 3 nickel 2 plus aqueous plus 2 Au solid. Now in terms of charge balancing, I can see that this is 0 for nickel, 6 plus for the gold, 6 plus for the nickel ions, and 0 for the gold solid. 6 plus is equal to 6 plus, so that's balanced. So we step away from the question. Have we produced a voltage of at least 0.50? Well, way past that, more than triple that value. I've done all of my evidence, I know all of my flows, and I have my net reaction. I hope you have enjoyed this lesson of You Got Hope Chemistry. See you next time.